Hello, I'm Safin and I'll be going over ports and processes on Linux in this video as part of the Linux Visually series. So what may seem like a really complicated system of files, processes, and services really boils down to a few key concepts that are analogous to a factory. Let's imagine that your computer is a gigantic factory with lots of machines for making just about anything. Let's say that one of the machines in the factory is a sewing machine, and that can be used to make t-shirts. Of course, these machines need to be operated by a human worker. In our factory, there's hundreds of workers, each operating their own individual machines. Some workers are making products that the factory needs to ship out to sell to customers, like our t-shirt. In order for a worker to start creating a product, they need to be informed about their task. Let's say that the factory decides it wants to begin the t-shirt manufacturing process. The factory will find a worker, assign them to a specific open machine, and give them instructions on how to use that machine to create a t-shirt. In this case, these instructions contain information on how to make t-shirts, as well as how to interact with the outside world. This is because customers who come to a factory need a unified way to communicate with the worker and exchange information or goods. What I mean by unified is that there should be a single way to communicate with the worker who you know is in charge of a certain manufacturing process. In our factory, we've labeled doors that customers know correspond to certain workers and their goods. In this case, door 10 is where customers know that they can ask for t-shirts and a worker will operate a machine to get it back to them, just like how it's shown in this example right here. There's kind of a lot of parts in this factory analogy, so I'm going to reiterate them before we go into how this models the Linux ports and processes model. I'm sorry that there's a lot of words in the slide, but it's absolutely essential that you understand each part of the factory before we switch over to its Linux counterpart. Feel free to pause the slideshow here and read these or go back if you're confused. Alright, so now with this analogy in the back of our minds, let's take a brief deep dive into what happens when you run a binary executable on Linux. If you're unfamiliar with what that is, or how binaries on Linux are managed, I'd highly encourage you to pause this video and watch my other video on the package management for Debian-based systems as part of the Linux Visually series. I would also encourage you to, if you're continuing on with watching this video, open up your Ubuntu virtual machine and follow along with me. You might not exactly be sure of the commands that I'm running, but stick with me and I'll cover them later in this video. I'm going to hop over to my virtual machine real quick so that I can also direct you, and yeah. So I'm going to just go ahead and open two terminals right here. So yeah, we've opened two terminals, and in one terminal, go ahead and run the ssh keygen command. I'm just going to run ssh keygen. I won't go through it, and you should either just wait right here, and this executable is currently running. But in the second terminal, what we're going to do is elevate to root. So do that with sudo. Oops, enter your password right here, and we're going to execute the ps command with the AUXF flag, and then grep for the string ssh keygen. So you'll run this command that I have on my screen right here, and it should show you something like this. SSH keygen. Here we go. So this should be what shows up. If we want to run the which command, which I'm going to do right here, if you run which and then ssh-keygen, that'll actually print the full path to the binary that's being executed when we run the ssh keygen command. But what really happened when we hit enter after typing that in this terminal? Well, the operating system kernel, which is Linux, received the instruction to execute this binary file right here, user bin ssh-keygen. In order for this binary to run, it needs to make use of the physical resources on our system, namely CPU processing power and RAM, which is random access memory, to both store and compute values. That's just the way that computers work. The operating system kernel, again Linux, has provisioned some of these resources, as in some of the hardware on our system, for this binary to run, and begins to execute the code in the file. This collection of resources, binary code, and other low-level details are grouped into what we call a process. Each process has a unique ID attached to them, just as you see right here. So SSH-keygen corresponds to the process ID of 5171. This grep is irrelevant because that's actually us calling the grep command here, so you can ignore this line. We'll just take a look at this one and see that the corresponding process ID is 5171. Does this process at all sound familiar to you? Because it really should. If we just go back to our slideshow here, you'll notice that this is how the parts of a factory kind of line up with the Linux model. The overall factory corresponds to your Linux kernel. It takes care of selecting parts of your memory and CPU for a process to run an executable, just as our factory informed a worker about what specific machines it should use to carry out their task. The instructions that a worker is given can be assimilated to the binary executable that the Linux process is responsible for running. And finally, the doors that workers can communicate with the outside world through correspond to both TCP and UDP ports, which we can just talk about as ports for now. And although we didn't see that our SSH keygen example, as in we didn't see the ports, we'll go over that and how they connect to processes in a future slide. So let's just move on for now. Now that you hopefully have a clearer idea on what processes and ports are on Linux, let's go deeper into the command that we ran earlier, which was this ps awkf command. The ps command allows you to list running processes, and the flags I've chosen here provide a tree-like view of running processes. If you're curious about their specific functionality, I'll highly encourage you to pause the video right here and check out the man page for ps to possibly even come up with your own combination of flags that you find easier for you to understand. These are just the ones I chose and the ones I've been using, but feel free to modify them as you wish. Well, regardless, we do still see quite a bit of information on each process. And the user is one of them. For example, the user that ran the process, it was actually the cpadmin user. We did not elevate to root in the terminal where we ran SSH-keygen. We also see the PID, which is the process ID. It's a unique ID for the process. The CPU and mem percentages are somewhat self-explanatory. It's just how much of the actual hardware is being used. Usually, well, in this case, the command is barely using any memory, so it's being rounded down to 0.0%. But keep in mind that modern computers do have lots and lots of random access memory, so I'm not really surprised by that. But yeah, we also see the actual command being run on the far right over here. However, the additional columns I'm not really going to focus on right now, but let's focus on the ones that I already mentioned, specifically the PID column. So as I said, each process has its own unique ID, which corresponds to the folder under the /proc directory containing information about the process. So the /proc directory, I'm just going to go ahead and go back to my virtual machine. The /proc directory is actually not a directory that doesn't physically exist on your hard drive. If you go to /proc, you'll see that it has a bunch of different folders in here, but this doesn't actually exist on your hard drive. It actually exists temporarily in memory, and it's what we call a pseudo file system. The implementation details of which you don't really need to worry about, but it's just something cool to know. However, we'll notice something interesting. Remember the process ID of SSH-keygen? We'll notice that there is actually a folder in here that corresponds to that ID, and it's right over here, I believe. So if we just cd into that process ID folder, we'll see a few interesting things. Before we go on though, if you're not familiar with the idea of symbolic links on Linux, I'd highly encourage you to Google or ChatGPT it before we go on. I'm assuming if you do have an understanding of symlinks, so we're just gonna move on. But of course, if you don't, feel free to pause it and do a quick Google search. So under this directory, I'm just gonna go ahead and full screen this. Under this directory, we'll see quite a few key files that can be useful if we want to identify how a process is being run. I'm gonna go back to the slideshow just because I have the key files here. And yeah, so this can be especially helpful if you've identified a malicious process and want to go about completely removing it from your system. The exe file in this case right here is actually a symbolic link to the binary that's being run as part of the process. In our case, is the full path to the SSH keygen executable. Remember, that's what we actually ran in the command line. If you saw that this executable happened to be some sort of malicious or unknown binary, you would probably want to take a look at what the executable is doing and maybe remove it, its containing folder, or maybe finding the program associated with it and uninstalling it completely so that all related executables and files are removed from the system. Next, the cwd directory corresponds to where a process is being run from. You see in this case it's also a symbolic link to not userbin SSH keygen, but rather home cpadmin desktop. And if you remember, we'll go back to the image right here. If I go back to this terminal, you'll see that I was actually in cpadmin's desktop folder when I ran this command. So that's what it corresponds to. It is worthwhile, however, to investigate the working directory of potential malware or unwanted program, especially if it points to, for example, a shell profile or a cron script. If you're not sure what those are, please feel free to Google them. But it's a good idea to take a look at those and ensure that any lines that correspond to the running process are removed, especially if you are suspicious of it. The CMD line file is, I'm going to go back to the image right here, and if I just do cat CMD line, you'll see it actually printed SSH keygen, and then the terminal prompt because there was no new line character. But this is the format it'll show up in. You can just ignore everything before this prompt. The SSH keygen is what's inside of this file. For example, if I were just to nano into it, that's what you would see. The CMD line file contains the entire command being executed to run the process. Now, note that this is not only the name of the binary, but also any flags associated with it. If you notice that the binary being run, or even the flags associated with it, are suspicious, you can search for the command being run using grep. You can grep under common directories where malware could be placed, for example, /etc. So for example, if this was something like a, I don't know, a netcat backdoor, you could go to etc and perhaps look for the specific line that's being run, for example, like this. And if you just recursively grep for this, then you might be able to find what's running this backdoor. And also a CMD line, you should pay very close attention to the flags because it is a common practice to rename malware binaries. And note that, just so you know, netcat is not actually a malware just in and of itself. It's just a networking utility, but it can be used as malware to set up what we call a reverse shell. So that's something you can research on your own time, but it's just be aware of that. But like I said, a CMD line that reads, for example, bin, for example, if we had something like, you know how the netcat line reads like this, if we had something like /bin/nice-lvnp4444, it should be like sort of looked into because we know that the netcat flags typically look like that, and we're not aware of what bin nice really is. So it's worthwhile to look into this binary. Just keep in mind the flags that are being run or flags that are being used to run the binary because they can lead you to potential malware. So yeah, be on the lookout for this. We're actually going to go over status on the next slide, but I wanted to make it clear that I added a further reading link right here. And it just has some more explanations on the files and some of the low-level details if you're curious. So yeah, feel free to access it via the video description. I'm going to put the slideshow in the video description, so if you would like to take a look at that, please do. But yeah, let's talk about status. So now the status file under a process's directory is also a useful tool for exploring a process. You'll notice if you just cat the status file, I'm going to go back here and go back to this proc directory. If we just cat the status file, cat status, you'll see a bunch of information about the process, and you'll see stuff like virtual memory, threading, capabilities, and a bunch of other cool stuff. But one thing to take notice of is that we'll see two lines that actually say PID in them, PID and PPID. So what's the difference? Well, PID is what we saw earlier, the exact process ID of the currently running process, but PPID refers to what we call a parent process ID. Remember our factory analogy? Well, it was missing one small thing, and that's the concept of process nesting. So I'm going to head back to the slideshow. So running processes on your Linux system actually corresponds to kind of a huge tree. And when processes are spawned, they aren't really added to sort of a huge linear pool of processes similar to our factory example. Instead, some processes can be spawned as what we call a child of another process. So, for example, Python in this case would be a child of systemd. So this is very similar to a file system tree on Linux, where some paths are children of others. For example, they're in a folder. But if you're still confused on this whole tree example, I encourage you to pause the video, and I've added this sort of research link right here. It's just a link to a Wikipedia page talking about the term tree in computer science, just because this concept is not only popular in Linux, but also everywhere. It's in computer science, it's in math. So just if you would like to take a look at this, it'd be probably something helpful to understand. So hopefully you've paused the video and taken a look at that, but I'm just going to move on. So the main point of this is that going back to the idea of child processes, all processes are sort of children of another. And what I mean by this is if we take a look at the proc folder corresponding to the parent of the SSH keygen process, so that would be this one right here. If we went to /proc/5145, we'll see that it corresponds to the bash process, which was running in our terminal screen when we executed this SSH keygen command. Remember, bash is an interactive shell where we can enter commands. If we cat status again, and we find the parent of this, and head to proc 5127. And by the way, your process IDs may not be the same as mine, but not to worry. You'll just go through the same process if you're doing this and following along. But yeah, you'll see that the executable corresponding to the parent process of bash is actually gnome terminal. Bash is running within gnome terminal, which is the actual process that displays this terminal graphical user interface on our screen. Now, if we go one process up from that, like right here, you'll see 1045. We'll head to proc 1045. We'll see systemd, and finally one more status. We'll see PID1. So one up from systemd, like I said, is what we call PID1, or the root process. The root process, which is shown at the top of this graph right here in this example, is the very first process that starts every time your system boots. And that's why we call it the init process. It's PID1. It's the first process that gets started. It manages the startup and shutdown of your computer, like the actual power. And every time your kernel spawns a new process, when, for example, you ask it to by running a command, it does so under this root init process, which is PID1, somewhere along the tree below PID1. So systemd, which we just saw, is what we call an init system, and that manages startup, shutdown, and running services. But I want to cover that in a future video because it's another complex topic, and I would really love to explain it, but not right now. We just want to talk about processes. Just it's important for now to understand that processes spawn under one another. You saw the hierarchy. Hopefully that made sense with the terminal example. Remember the command that we ran within bash, within the terminal, etc., all the way back up. Now, the reason why this is useful is that if you're confused about how a process is being run, you can actually investigate upwards on the process tree to see what exactly is spawning it or running it. Remember how I mentioned earlier that the ps command with the arguments I added shows running processes in a tree-like manner? Well, this is exactly what I meant. Note that this representation is way easier to visualize than what we just went through the process of going upwards via the parent process ID over and over and over again. Obviously, you never want to do that if you're a sysadmin. It's a waste of time. So this command does that for you. And I'm going to go ahead and I'm not going to run the command again on my virtual machine, but you can feel free to do so on yours, just because it's a little bit to type out. Really what I'm doing here is I've added the -B3 flag right here, which sort of prints the 3 lines before the match that grep finds. And this is equivalent to just scrolling up, basically, if you ran pxawkf without piping it into grep. It's just like an unfiltered output. notice you'll notice that the processes we saw while walking up the parent process tree via the status file and going up and up and up are actually shown right here very conveniently. And like I said, this is useful when finding and exterminating malicious services on your system because it can give you more information on what exactly is causing it to run, like what process, the parent process, is spawning that child potentially malicious process. Please note, and this is extremely, extremely important, so much so that I decided to dedicate an entire slide to it, that even if you've deleted the binary executable associated with a running malicious process, as in you've deleted that file that corresponds to the exe file in that proc folder, you must kill the process associated with it to completely stop. This is because when an executable is run, like user sbin ssh keygen or whatever the path was, it is sort of loaded into your random access memory temporarily as it executes. So it's even if the binary is deleted from the disk, it will actually still run. And this is sort of important to keep in mind. So I would just recommend that if you would like to completely kill the process, you must do this using the kill command to send what we call a termination signal to that process. So you can do this by running kill followed by dash and the signal you want to send, as well as the PID you want to send the signal to. So for example, if you wanted to completely destroy the process without a graceful exit, you could use kill dash 9 followed by the process ID, and that would completely kill it. If you want to send a different or more graceful signal, you could send something like sigint to emulate Control C behavior. It would be just like if you ran Control C in the command line. And you could use kill dash 2. So for example, if I hop over to my virtual machine right here, and remember that our process pxoxf grep ssh keygen was actually 5171. If I run kill dash 9 and then that process ID, you'll see that this process right here, it was killed and it just completely stops. If I ran Control C when I was doing this, it would show Control C right here. If I run, for example, kill with the sigint signal, it would have the same behavior as running Control C. I mean, I added a signal reference here to the slide for the different signals you can like send to a process, but you're mostly going to be using kill-9, especially if you're sure that the process is harboring some sort of malware or it's unneeded or something like that. So yeah, I've added this reference. Feel free to click on it if you, like I said, the slide will be in the description. So yeah, I would encourage you to read through that to get a better idea of what I'm talking about. So wow, that was a lot of information. Hopefully you caught most of it. Feel free to pause, rewind, or ask questions in the comments if you're confused at any point. But now we're going to take a brief and simple look at ports and how they correspond to processes. So remember this slide where we talked about how a worker could communicate with customers through a door? This might be useful if we're selling something like t-shirts, but from a Linux perspective, it could be helpful if you're doing something like hosting a website, for example. Imagine that some user on the internet asks to access https://www.safin.dev. Now, let's say I have an executable binary running on my PC, which is sort of listening for users to ask to see my website. And that's me right here. I'm waiting for someone to connect to me from port 80 or 443. Now, you may have heard that HTTP is associated with port 80 and HTTPS is associated with port 443, but for the purpose of this video, what HTTP and HTTPS are really does not matter. All that matters is that in this scenario, someone out there is asking to access port 443 on my PC so that they can speak to the executable binary and see the web page that they want to, which is safin.dev. Now, I've replaced, the user's computer will turn safin.dev, this link right here, into a bunch of numbers that uniquely identify my computer on the internet, but I've just replaced that with Safin's PC just to reduce some complexity. So let's just say he knows how to get to me. Now, the user's computer, like I said, will take care of that, but see, I've replaced it. So yeah, next it specifies the port that they want to access because they assume it'll give them some valid content. So they assume that my PC on port 443, if they knock on port 443, then I'll probably give them some sort of actual response. Now, when my PC receives this request, it actually first has to check whether that unique port is opening and listening for connections. Now, in our factory, this is analogous to having a door in the factory that a worker has instructions to receive and send messages to and from. If there's no worker assigned to a door, nothing will happen if a customer knocks on it. Similarly, if there's no process running an executable with instructions to send and receive input from a port, nothing will happen if a user tries to access it. To clarify, the person writing the code for an executable will actually have to specify if they would like it to have this behavior and listens to connections on a particular port. So that's implemented by the programmer. Not something you need to worry too much about, but only a single process, this is important, only a single process can be bound to a specific port, just as a single worker can only manage a specific door. Note that technically a single process can bind to and listen on multiple ports, but not the other way around. So I could listen to incoming connections on port 80 and 443, but no one else on my PC, if I was, or for example, no other worker in the factory could also try to receive and send information on doors 80 or 443. So hopefully that makes sense. But why does this matter for us? What's the point of knowing what processes are bound to what ports? And that's a great question and a valid one at that. However, one key takeaway from the last slide should be that an outside user can only access some process on our computer over the network by connecting to a specific port. Now, this is awesome when we're running programs like web servers or file servers where we want people to access them intentionally. As a result, knowing what ports are open and listening for connections is a great way to take inventory on what's available to the outside world for a computer. Remember, the outside world doesn't only include your customers, it also includes your adversaries, so be aware of that. And like I said, it only ports are for accessing content over the network, and really that's the only way that a malicious actor could access your system, because if they do have physical access, then you have much bigger problems. So moving on, like I said, it is very important to know what ports are open and listening, and to take inventory of them. Remember, yeah, that would be very important. Now, this is where the ss command, ss-tulpn, can be very helpful. I've just collected these flags. This combination of flags is extremely powerful in taking inventory of listening ports on your system, because it not only shows you the ports that are being listened to, but also the process associated with it. You can see the exact process name as well as the PID associated with that process. Now, there's no point of running this on my virtual machine because SSH keygen is not accessing anything over the network. However, if I was running something like Apache, it would show up here. And I'm actually just going to go ahead and install that in the background so I can show you what it looks like. So I'll just apt install Apache 2, continue. So right when this is done installing, we can actually check out, oops, not -ss, sudo -s, password. And now this is done installing, and we can just go ahead and run ss-tulpn. We full screen this. We'll see that something is listening on port 80, and that would be Apache 2. So that sort of makes sense. This program right here is a web server. It's similar to the one that I described in the previous slide, and it allows you to access some content over the internet. So if I were to go ahead and access my sort of local host, what it would do is it would show up as, oops, localhost. It would show up this, or it would show this Apache 2 default page. And yeah, like I said, if we just add, whoops, localhost :80. What's happening here is it's accessing port 80 on my computer, and it's returning the data just as I asked for, similar to how I explained on the previous slide. Now, that is extremely powerful because using what we just learned about the ps command, you can actually investigate suspicious processes and ensure that ones that are required by company policy or scenarios are functioning properly. So, for example, if you saw a rogue service or a rogue port being accessed, you might want to take a look into the process associated with it, and you can also use this to check whether the processes that it needs to be running actually are running. So yeah, you could do that with this command, and you can also investigate the proc folder like this. So yeah, hopefully now you have a better, more powerful port and process management toolkit that'll help you better take inventory of your system. Finally, I want to leave you all with some guidance on how to use this information, especially in a cybersecurity context. On the tip side, I highly encourage you to thoroughly take inventory of your system, especially if it's a compromised scenario, and see what ports are listening and processes are running. Using the PS and SS commands along with the flags that I already mentioned earlier, or your own combination with anything else you find to gather information is sort of the main idea of what you want to do. Next, it's a great strategy to take baselines on a uncompromised scenario, perhaps a clean install of the operating system you're dealing with, or a snapshot of it before it was compromised, and compare the inventory you've taken. That would be the running ports, the running processes. See which ones are present in the compromised scenario versus the uncompromised one. Finally, your goal, especially in a company setting, should be to always minimize attack surface. If you notice a process or port running or open when it's not needed, it's worth taking a look at to potentially removing, even if it's not critical for your, even if it's not necessarily malware, if it's not critical for your system to function. Please make sure to thoroughly research whatever you're looking into before you nuke it, of course. But yeah. Last, some further reading, which I think is useful. These aren't links, but they're more like topics that I would encourage you to look at. Yeah, so regarding the TCP and UDP stuff, if you're interested in networking, I mentioned these two earlier when talking about how Linux and our factory model correlate, but I didn't go too much into the distinction between these protocols, so if you would like to read more about that, I would encourage that. It's definitely a cool and interesting topic, and it'll be useful to you, especially if you go into computer science. Next, I would encourage reading more about cron and at, which I also briefly mentioned. These are ways to periodically run tasks on Linux, and they're commonly used to routinely spawn processes that you may not exactly want or need on your system. As for systemd, I'll likely go over that and services in a future video because this topic sort of builds to that. But as always, doing your own research is highly encouraged. So yeah, thank you guys. I hope you've learned a lot from this video. As always, please let me know if you have any questions or comments in the comment section. I would absolutely love to take a look at and respond to all of them. But yeah,